Hi, I'm Daniel Amir, and I'm here to present Shale, a practical, scalable, Oblivious reconfigurable network. Data center network demands grow at an extremely aggressive rate. Google has reported that in their data centers, the bandwidth demand doubles almost every year. And Microsoft has reported similar scaling. The link rates that they deploy in their data centers increased 400 times over the 10 years ending in 2020. And in part, they accomplished this by transitioning to optical links. On the other hand, the actual switch chips that we use to implement our data center networks are only doubling in speed every 2 years, following Moore's law. And it's worrying that the semiconductor industry is having trouble maintaining Moore's law, which indicates that even this scaling in switch chips may not be able to be maintained into the future. This motivates us to look for an alternative to packet switches, namely optical circuit switches, which have a few advantages. First of all, packet switches, as we've transitioned to optical links, need to convert that into electricity to process it, which means they need expensive optical transceivers at every single switching stage, whereas circuit switches can route the data while it's still in light form. Additionally, while packet switches are limited by Moore's law, circuit switches are potentially bandwidth agnostic. Because they're moving light from one place to another, you can upgrade the surrounding network around them and sometimes still use the same physical circuit switch design even as you're upgrading the network speed. However, there are a few drawbacks. First of all, they're not as easy to use as packet switches because you have to tell them which circuits to deploy. But more importantly, in today's data center networks, sending a short message may take you only tens to maybe 100 nanoseconds to send that short message at today's fast link rates. But circuit switches used to be really slow to reconfigure, taking a few milliseconds. That makes them really inefficient at supporting short flows. However, we now have designs for optical circuit switches, which can reconfigure in just nanoseconds. And that motivates us to ask, can we now design a data center network that only uses these nanosecond scale circuit switches without using packet switches? So, in order to answer that question, let's first think about how traditional circuit switch networks are designed. First, we have all of the nodes in the system think about the demand that they want to send, and we collect that demand somewhere, compute what are the best circuits, and then we tell the circuit switch, here, make these circuits, and then we can send our data. The beginning part of this control loop, where we collect an info about the demand and try to be smart and set the circuits dynamically, that part is too slow. It cannot work at nanosecond scale, even if we have those switches available. So instead, we need to reconfigure the network oblivious to the current demand, which is what Oblivious reconfigurable networks do. Instead of taking into account the demand, they pre-schedule the circuits that they're going to deploy at any point in time. And then, as we're iterating through the schedule, we can iterate through it very quickly because we can reconfigure on the scale of a couple of nanoseconds. We only have to stay in each line of the schedule for maybe a few tens of nanoseconds in order to transmit some data, and then we reconfigure. So we're actually finally able to take advantage of our new fancy nanosecond reconfigurable switches. So there are several Oblivious reconfigurable networks that exist, and I want to highlight three, Rodina, Shale, and Sirius, which all have a very similar design using a single round-robin schedule. And the way this schedule works is like, here are the same 5 nodes that were attached to the switch before, but now I'm going to show the schedule a little bit more logically. We can see that they're connected to each other in a round robin. And the way that you send data on this is, let's say node A only wants to send to node B. In the first time slot, we can send directly. In future time slots, we do still want to make use of that bandwidth. So what we're going to do is we're going to send indirectly using these intermediate nodes and having them eventually forward it to node B. And as you can see, we're able to use all of our outgoing bandwidth at node A, and eventually all the data gets forwarded to node B. This is an example of a strategy called Valiant load balancing, where instead of sending directly to a destination, you send first to a random intermediate node, and then from there to the destination. And that helps us utilize all of our available bandwidth, even on an unbalanced workload. And that means our throughput is always going to be at least half of the line rate. And it's half of the line rate because half of our hops are for the first hop, and half of our hops are the second hop, which actually reaches the destination. And that's true for all traffic patterns. That's actually really good for ORNs, but what's not so good is the latency, which is OFN. Remember here when we sent a cell via node D, and then we had to wait the entire schedule to iterate before we could then finally forward it to node B. And this is fine if you only have 5 nodes and it only takes you 4 time slots to iterate through your schedule. But if you have 100,000 nodes and you have, then that's going to be really bad. You're going to wait 100,000 time slots. Even if you have time slots that are just 5 nanoseconds long, like Shale uses, the latency is still going to be half a millisecond, getting us all the way back to traditional circuit switch designs almost. So additionally, there's another problem. If you're connecting to so many neighbors, you have to maintain state for all of those connections, and we found that this can require multiple gigabytes of on-chip memory. So we then ask, can we do better? And this is where our paper comes in. We developed Shale, a new ORN design that supports tens of thousands of nodes and achieves orders of magnitude better latency and memory requirements than the existing designs at these scales. We achieve this by using new schedules, and these schedules bring us a tunable trade-off between throughput and latency, and a previous theory result that we have has shown that each of these trade-offs is Pareto optimal for ORNs. We enable this design using a new congestion control which is tuned to Shale's unique context, and we also extend this congestion control to address node and link failures. We also have an optimized FPGA-based hardware implementation. And finally, we show how you can interleave different schedules of Shale in order to achieve a combination of the low latency of one schedule and the high throughput of another schedule. So first, let's start with what are these schedules? What is the Shale schedule? Well, we generalize the existing round-robin design. Instead of having one big round-robin, we have multiple shorter round-robins. So I'm going to show you this visually. Here's the round robin that we had before, and now I'm going to show it to you again, but this time only looking at the nodes that node A connects to. So this is that same round robin. Now I'm going to show you a bigger round robin with 16 nodes. And you can see that that took a long time. And now I'm going to rearrange these nodes into 4 groups. I'm also going to relabel them and color them different colors. And now looking at node 0, 0 in the top left, first we're going to do a round robin within the same group, and then a round robin with nodes in the same color. So first in the same box, and then in the same color. And you'll notice the neighbors in the same box have a different x coordinate, and the neighbors with the same color have a differing y coordinate. So in the first round robin, we can send to any x coordinate, and then we can send to any y coordinate. In general, direct paths are now going to take h hops, 1 hop for each of the h coordinates. We do still want to use Valiant load balancing, so a full path looks something like this. Let's say we want to send to node 3, 2. First, we're going to take 2 spraying hops, we call them, to reach the intermediate node, and these are randomly determined hops, 1 in each coordinate. And then we're going to take 2 direct hops to reach the final destination. The latency is going to be way better than existing systems. Instead of being O of n, we're now O of square root of n or cube root of n, depends on what you set h to. The throughput is going to be reduced, so let's see how this looks, kind of put some numbers to it to see if this is a worthwhile trade-off. Here, this chart shows different tunings, including existing networks, which are just a special case of Shale when h equals 1. The x-axis shows the throughput, which is a fraction of the line rate. The y-axis shows the intrinsic latency, or the latency purely due to the schedule and routing scheme. It's ignoring things like queuing delay and propagation delay. We'll get to those later. And ideally, we would like a high throughput and a low latency. As you can see, existing systems are really bad in the latency department. They have a latency of 100,000 time slots at this scale. And if we just use the same 5 nanosecond time slots that, we use in our evaluation and that Shale uses in their evaluation, we can see this is over half a millisecond of latency. By going to h equals 2, we get almost 2 orders of magnitude improvement in the latency. And if we go to h equals 4, we get almost an additional order of magnitude improvement. So even though we're losing out on the throughput, the latency improvement is huge. So this is really an interesting trade-off, especially later when we'll talk about interleaving. You can potentially mitigate the throughput reduction. But in order to enable this to actually work, we now need to talk about queuing in our congestion control, because queuing delay actually does exist in real systems. So let's say we have these 2 cells that we want to send, as an example. Notice that they're being sent to different destinations. One is being sent to node 3, 2, the other one to node 3, 3. Let's say we happen to spray them via the same intermediate node. Well, it just so happens that now in their first direct hop, they want to take the same direct hop via this node 3, 1. So we have to pick one to send first. Let's say we send the orange one first. So that one's going to arrive at its destination on time, but the red one has to be delayed for an entire schedule iteration before we get another time slot headed to node 3, 1. So this highlights one issue with queuing that exists in ORNs, which is that the queues, we are much more sensitive to queue lengths, because the queue is empty way slower than line rate. They only send 1 cell per schedule iteration. Additionally, each flow has a huge numbers of paths that it used thanks to the packet spraying that we had before due to VLB. Unfortunately, this is kind of necessary for ORNs to be successful, as we show in our theory paper that I discussed before. And this means that a lot of congestion control mechanisms that we have in existing data center networks don't really transfer well to the ORN context. Now, existing ORN designs do have a pretty elegant congestion control, but it was kind of highly linked to the fact that their path lengths were only 2 hops long. And in Shale, they don't transfer well, because in Shale, congestion can occur far from both the source and the destination. So we create a new congestion control mechanism. In creating our mechanism, we focus on two types of congestion. First is path collision congestion, which is when two cells headed to two different destinations happen to both want to take the same next hop. This is like the example that I showed in the previous slide. The other type of congestion is egress congestion, which is when multiple cells headed to the same destination all want to use the same queues to reach that destination. We have two different strategies for both of these. First, path collisions. We use a strategy called spray short. Here, let's say that we have this orange cell and queued at node 1, 1. It wants to take this next hop. And now let's say we're spraying this red cell also via node 1, 1. We sprayed it on the y coordinate. Now we want to spray it on the x coordinate, and we want to choose this randomly because we're doing valiant load balancing. What if we randomly chose this one? Well, then we'd have to be queued behind the orange cell. So what spray short says is let's not choose that. Instead, choose a spraying hop that has the shortest queue. Now, this does mean we're not quite doing valiant load balancing anymore, but in practice we see that this does not hurt our throughput. In fact, our throughput actually looks a little bit better, and we have much better performance in our queuing as well. And in our paper, we give some intuition as to why we think this doesn't actually cause any problems in practice, that we moved away from pure valiant load balancing. Now, for egress congestion, we have a hop-by-hop congestion control mechanism. Once a node sends a cell via a given intermediate node, it's not going to send any more cells along that same path, headed to the same destination, until it receives a token from that intermediate node. So when does it receive that token? Once the intermediate node has sent that cell on its next hop, then it will send a token back. So to give an example, let's say we're sending from node AA to node CC. First, we're going to send a cell on a spraying hop to node BA, and now we're not going to send any more cells on a spraying hop to node BA that are headed towards node CC until we receive a token back. And this is going to happen again for all of the subsequent hops. And what this does is it prevents cells from piling up at the final queues headed towards the destination. Now you'll notice that each of these tokens has the destination as well as a number, which represents the number of remaining spraying hops. The reason we do that is because this prevents circular waiting, which means that this is a deadlock-free congestion control system. Additionally, we use special push and extract out queues to prevent head-of-line blocking. Okay, so now let's talk about how we have evaluated this. We've done it through extensive packet-level simulations with 10,000 nodes. Here are some simulation parameters that I'm not going to read off. And we've also used several different congestion control mechanisms to compare to. First, we have our congestion control mechanisms. Here are the names that we're going to use for them on the graph. We have spray short, we have hop by hop, and we have a combination called HBH spray. Additionally, we have competing baseline where we basically just, at each queue, prioritize cells from short flows. We call this prio. We also have an idealized clairvoyant sender-driven congestion control where nodes telepathically know about all the other senders in the system. We call this ISD. And finally, we have a receiver-driven congestion control called RD. And we also add packing tripping to make a congestion control system we call NDP because it's basically a version of NDP that's transposed into our Shale context. Okay, so here is the first workload that we're going to look at, which is a short flow workload that primarily creates path collision congestion. And you can see that spray short is doing really well here. It's reducing the congestion, which we can see in the top graph, and it also has really short flow completion times, as we can see in the bottom graph. But if we combine it with hop by hop, we get even better performance. And we can also see, once I add in the other baselines, that we outperformed all of the baselines for this workload. Then we have a heavy-tailed workload, which creates egress congestion, and here the congestion is much, much worse. So I had to convert to log scales on the y-axis. You can see that hop by hop spray is doing a pretty good job on both the queuing and the flow completion times, especially in h equals 4. Once I add in the baselines, you can see we are still the best for h equals 4. In h equals 2, we are outperformed by ISD, but remember, that one has the nodes telepathically communicating, so I do feel this is a very impressive result. NDP is beating us for h equals 2, but only slightly for the flow completion times, and we are significantly outperforming it on h equals 4. Okay, we do also extend our hop by hop congestion control to address failures by introducing invalidation tokens. These have the same format as regular tokens, and they indicate that certain links are no longer working or that certain paths are no longer usable. We use this to route around those failed paths and links, and what we show is, through simulations, even when we do this, even when we have failed nodes, our throughput doesn't suffer too dramatically, and that's important because we are doing indirect routing, so failed nodes could potentially impact throughput. Additionally, now I'm going to talk about our implementation a little bit. We have a prototype based on an FPGA NIC, and we add several optimizations to reduce the memory requirements. Please see the paper for those details. The key thing I'm going to show you is this graph, which shows that we use orders of magnitude less memory than existing systems. Finally, I'm going to talk a little bit about interleaving. We literally interleave two different schedules to create a combined schedule, and depending on the proportion of time slots that we allocate to each subschedule, we're going to increase the latency inversely proportional to that value, although this is only the intrinsic latency that gets increased. Propagation delay doesn't change. Queuing delay may change if you're routing different traffic because now it's interleaved. Additionally, the throughput of the subschedule is going to be reduced in proportion to the proportion of time slots that you gave to that subschedule. However, the overall system throughput is just going to be a weighted average of the different subschedules. So really quick, here are some comparisons where we're interleaving between two different schedules that we have in our paper. We're interleaving between a blue schedule and a yellow schedule. And you can see here are the interleaved versions, and you can see the short flows are achieving much better latencies than the low H schedule for short flows, and the load factors, the throughputs that we're achieving, are kind of compromises between them. So in summary, I've presented Shale, which is a new ORN design that supports tens of thousands of nodes, and at this scale, it achieves orders of magnitude better latency and memory requirements. We have new schedule. We do this by using new schedules that are tunable to achieve a tunable trade-off between throughput and latency. All of these trade-offs are Pareto optimal for ORNs. We enable this using a new congestion control mechanism, which we extend to address node and link failures. We also have an optimized FPGA-based hardware implementation, and we support interleaving to combine multiple tunings. Really quick, here are some related theory works that our group has done. In case you are interested, please pause and you can follow these paper titles to find them. And finally, I'd like to thank my co-authors on this paper. I couldn't have done this without you. And I'd also like to thank you for being interested in this work. Thank you.